Okay. Hi everyone. I hope you hear me. If you hear me, then please tell me. Yeah. We'll be talking about problems A to E, because I haven't solved F. As you can see, only like 4 people solved it in Div 2, so not much. Yeah. Although I will be back to master after this contest if nothing will get wrong answer on full system tests. I failed just out of master, so I think I will be back. Okay, so do you hear me? That's nice. Let's solve A to E, but we'll wait maybe 2 more minutes or something. I think today problems were really easy. Like, I don't know, maybe the solve numbers doesn't show that, but I think D and E were really easy for like a typical div 2. Like, they were not hard, they were easy. Or like CDE, they were all really easy. Okay, let's start from problem A. I hope you hear me well, because sometimes I think I can be heard like I was in a cave, so that's weird. Okay. So problem A. Yeah. CP class in a cave. Like, I have another microphone, so you can tell me which is better. Wait. I will now switch my microphone and you will tell me which is better. Wait. So now, is it better or worse? It's better or not? Worse. Okay, so back in the cave, I see. Yeah, I have to do something about it, but I don't know. Yeah, cave is super fun, right? So now you should hear me in a cave, right? Okay. So let's solve A. In this problem we are given two numbers. N and K. And in one operation we can take some A and subtract K to the power of A from N, right? So do N is equal to, so we can do N is equal to N minus K to the power of A. And we want to say how many operations do we need to make N equal to 0, right? Okay, so, well, the observation is that the greedy works, and like I don't think I will prove it, but I think it's obvious. Like the greedy works here because like we have this some like items like k to the power of 0, k to the power of 1, etc. And like each item can be described as the sum of the previous items, maybe multiplied by something, right? So yeah, that's why it works. Okay, so now what we'll do is just we'll process all the powers of k, so like k to the power of 0, k to the power of 1, all the powers of k such that ki is smaller than n, right? And we'll just do greedy. How to do greedy? We are going from the greatest to the smallest powers, and when we have some ki and we have our n right now, then we can notice that the amount of these items that we will like pick to our solution is n divided by ki and the floor of that, right? So we'll pick this many kis, right? And we'll add this to our answer and like do n is equal to n modulo k to the power of I, right? This is some basic math. So I don't know if I should go any deeper. This is like very easy task. Do you understand? Yeah, it is like a representation, like binary representation. We are basically what we want to do. We want to translate n, that is in decimal representation, to some representation in base k, right? So it can be, if k is equal to 5, it could be, for example, 4, 0, 1, 3, 0, and 2, let's say. Then we would just like to find the sum of digits. I've seen solutions that go like this. While n is different than 0, answer plus equal n modulo k, n divided by k. Yeah, this is basically what we are doing here. We are just representing a in like cave basis. Yeah, basically like we want to represent n in cave basis. So this is like another maybe easier even approach, is that I want to represent n in the representations with base k, right? So to find the last digit will be n modulo k, right? Because this is just how bases work. And then to like delete the last digit, we need to divide with floor. I don't know, this is just how bases work. So yeah. Yeah, I can repeat one more time. So basically, one more time, we want to represent n in the base k, right? So we have like k to the power of 5, let's say, k to the power of 4, k to the power of 3, k to the power of 2, k to the power of 1, k to the power of 0, right? And I want to like give a number to each of those powers, such that like when I will let's say I give a numbers like this. So I want to do 3 times k to the power of 5 plus 1 times k to the power of 4, right? This is my representation, and I want this to be equal to n. So basically to find, and then our answer will just be, you know, sum of these, right? So basically what I want to do is I want to notice that the number that I will have near the k to the power of 0 is just n modulo k, right? Why? Because all the other powers are divisible by k. So what will be left is n modulo k, because this is like the only part that is not divisible by k. So after that, I want to just do, so I want to add this to answer, because this is our last digit here, and after that I want to do n is equal to n minus n modulo k, right, because I already added this. And now I want to notice that, well, I can just divide all the powers here by k, and divide n by k, because n is now divisible by k, and just repeat my process. So I will do n is equal to n divided by k. So basically, yeah, this is it. And as some of you may know, this is basically dividing with floor, those two operations. So yeah, that is it. We are solving problem A. I don't think I will go deeper into it because, well, it is problem A. I think almost everyone solved it on the contest, right? It's not like, yeah, 11,000 people, I think. So, yeah. Let's go to problem B. Yeah, because this is A, so. In this problem, we are described a process, like we are given a processor, I don't know. We have n light bulbs, like 1, 2, 3, 4, up to n. And basically, in the beginning, all of them are like, let's say, blue, or they're lighted up, right? Or they're turned on, sorry. And now for each eye, okay, let me assume that n is 8 and show you the process. So, we have 8 bulbs, or light bulbs, let's say, and in the beginning they are like all turned on. So I will say that they are turned on if they have this blue circle over them. And now for each eye from 1 to 8, we are doing such thing. We are looking at all multiples of I. So we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. We are looking at all those numbers, and for each number we are looking at we are looking at all its multipliers, or I don't know how to say it in English, but like the numbers that such that they are divisible by 1, the numbers such that they are divisible by 2, etc. So, for example, for 1, we are looking at all its multipliers, and we are switching their state. So for each number we are switching its state. So we are saying for each number that now they are not turned on. Then we are looking at multipliers of 2. So that will be 2, 4, 6, and 8. And for each of these, we are changing their state. So we will turn them on because they are not turned on. Then for each wait, let me quickly see how this is in English. Oh yeah, so for each multiple of 3, so this will be 3, 6, and 9, etc. But we don't have it because we assume that n is 8. We are changing their states. So for 3 we are turning it on, and for 6 we are turning it off because, well, it was turned on. Okay, so now 4, well, we have 4 and 8, they're both turned on, so we are turning them on. We are turning them off, sorry. Then for 5 we have only 5 and we are turning it on. For 6 we have well, 6, so we are turning it on, then 7 and 8. Because, well, 6 is the only multiple of 6, 7 is only multiple of 7, and 8 is only multiple of 8. Okay, so now we want to say, I was looking for the word multiple. So now we want to say, and we say that for n equal to 8, our answer is equal to 2, because our answer is equal to the number of bulbs that are not turned on in the end. So we want to say, what is the smallest n such that answer from n is equal to, answer from 8 is equal to 2, is equal to k, and k is up to the 10 power of 18. So we want to say, what is the smallest n such that the answer for it is equal to k? Yeah, so what is the smallest n such that the number of bulbs that will be turned off in the end is equal to k? Do you understand the statement? Okay, I hope you understand this. So, well, let's notice something like this. For number x, we have some number x, right? When it will be turned off in the end, and when it will be, like, for some number x, we can notice that all its divisors will be changing my state, right? So if I have, for example, 3 divisors, if x has, let's say, if x has 3 divisors, then first it will be turned on, then it will be turned off, right? Then it will be turned on, and then it will be turned off, no matter what these divisors are. So we can notice that the only thing that determines, like, if x is turned on or turned off is just the parity of number of divisors, right? Because if x has odd number of divisors, then it will be turned off in the end. And if x has even number of divisors, then x will be, for example, 4. Like each arrow is a divisor, right? It's like changing of state, so divisor. So if x has even number of divisors, then it will end up being turned on. So now we just say that answer from n is just number of, okay, let me write this with my keyboard, because I'm not really good at handwriting. Answer from n is just number of numbers at most n such that they have odd number of divisors, because that's when they end up turned on, right? I hope you agree. Because the only thing that changes my state is some divisor, and if I have odd number of divisors, then I have odd number of changes of state, otherwise I have even. So, yeah. And what are the numbers that have odd number of divisors? Well, as some of you may know, if I have some number a, and it is equal to p1, if I will look at the, how to call it, like, factorization of a, right? Then, as some of you may know, it is like an easy combinatorial formula. The number of divisors is just alpha 1 plus 1 times alpha 2 plus 2, etc. Okay. Right? You see, oh no, sorry, stupid thing. Times alpha n plus 1. So, this is our formula. Why? Because we can pick the... If we take some divisor, then for each pi we want to pick how much of it we will take. And we can take, for the first divisor, for example, you can take 0 of it, 1 of it, 2 of it, up to alpha 1 from it. Right? So we have alpha 1 plus 1. And we do this for each prime number. So that's how we get this. This is number of divisors. Number of divisors of A. Okay, this is it. Yeah. So when this will be odd? Well, it will be odd if all A's, or alphas, sorry, are even. Right? And as some of you may know, when all alphas are even, our number A is a square of some number, right? Because it will be A to the power of P1 to the power of alpha. Yeah, we'll have this. And now we can just say that square root of A will be just all those. It will just be all those numbers divided by 2, right? Because this is what square rooting is doing. It's like multiplying this by 2 or dividing it by 2. So now what we are doing is we have noticed that the answer from n I have done something wrong here. Oh, okay. We want k bulbs to be on. So we want n minus the number. Yeah, we want n minus answer from n. That doesn't change anything. So we want n minus answer from n to be equal to k, sorry. Because we want bulbs that are on, and answer from n is the bulbs that are off. So now we have shown that answer from n is just square root of n, because those are just some square roots. Okay, if camera is not clear, then wait, I can make it clear. Yeah. Okay, so yeah, answer from n is just square root of n, because, well, the only bulbs that are off are the bulbs that are squares. So n minus square root of n, we of course are taking floor of it, right? Because, for example, if n is equal to 11, then square root of 11 is I don't know, it will be something like 3 point something. And we have 3 numbers that are squares and are smaller than it, right? 1, 4, and 9. So we are taking floor of it. We'll be taking floor of it. Yeah. So we can binary search over it. Just because we see that this is increasing, obviously. And we can binary search over it. And to find CIL of square root, we'll also binary search over it. I think this is standard. We are just shooting in the middle if we want to find CIL of square root of n, right? So we will just shoot in the middle. Let's say that we are checking because okay, what we want to find? We want to find the greatest such x such that x squared is smaller than n, right? We want to find how many squares we can get. So we'll just shoot in the middle and check if middle squared is smaller than n. I can show you my code quickly. And then we'll go to harder tasks. Sorry. That is quite weird. No. Where is my B? That's quite weird. Okay, it's here, let's say. So yeah, basically I wrote a function get a squared that takes number x and look out for the greatest such number such that its square is smaller than x, or like at most x. And then just binary search over answer. So we have two nested binary searches. So the complexity will be log squared. Yeah. Do you have... yeah, I did consider the squared, like you have function that gets a squared here, right? I'm just looking for the smallest such n such that it minus the number of a squared s is like k. This is just binary search. We are just binary searching over n minus square root of n, and in this we are binary searching over the square root of n. I have not used math as squared because I don't know how to use it. When I need a squared, I always like write bin search. Yeah, I never use it. I always just write bin search. Okay. Yeah, well, I think my binary search is not much slower than in booled squared, so it's okay. I just used binary search to get a squared. You just binary search and look for the greatest. You look for the greatest square such that it's good. Okay. Let's go to problem C, I think. Yeah. I think we spent too many times on those really easy problems. Like, I am getting too much into detail, but let it be. So now for problem C. In this problem, let me write it. Oh, I solved it very, very stupidly. Like this problem. See, I just test this. In this problem, I just tested all the cases, but let me explain. So in problem C, we are given three numbers, B, C, D, and basically we want to find such A's. We want to find A such that A or B minus A and, sorry, I don't know, maybe I will write A or B minus A and C is equal to D. So we can, if you have something like binary operators, then you can just look at this problem, like for each bit you can solve this problem like separately. So let's look at some bit. Let's look at bit k. I will say that bk is just the value that b has on the kth bit, right? So we have like 4 or even 8 cases. Let's start. If bk is equal to 0 and ck is equal to 0, then if I do ak equal to 0, like I have 8 cases, right? If bk is equal to 0 and ck is equal to 0, then if I set ak equals 0, then I get what? Here I will get 0, because 0 or 0 is 0, right? On this bit I will add 0 to the left side and obviously 0 to the right side too. And if I will set ak equal to 1, then ak or bk is equal to 1, obviously, and ak and ck is equal to, well, 0, 2. To 0, right? So I will get 1 here. Do you like understand my logic? Yeah, I got super stupid voa. Like, I just didn't have longs here. That's what happened. I need long here. And, well, I considered all the cases like this because it was easiest for me. I know that you can probably notice that you can take some XOR or something. I don't know. I don't need it. And, well, you can just do all the cases like this. I will maybe write one more case for you, and I hope you will get all the other cases by yourself. So if bk is equal to 0 and ck is equal to 1, then if I set ak equal to 0, then ak or bk is equal to 0, and ak and ck is equal to 0 too. So then I get 0, because I get 0 here and 0 here. And if I set ak equal to 1, then ak or bk is equal to 1, because ak is 1, and ak and ck is equal to 1 too. So here I will also get 0, because I will get 1 minus 1, right? I hope you understand. And you can get all the cases like this, and just for each bit, if we have also decay, then we pick the good value from the right side here, right? You understand? This is like a really, I don't know, not smart task. Oh, wait. Yeah, I don't. Yeah, this is not a smart problem for me. Maybe there is some beautiful ad hoc solution we can see. Yeah, they basically have the same solution as me, right? They just look for the all 8 possibilities, and, well, that's just it. This is like stupid. Just you also have to write such a formulas for bk equal to 1 and ck equal to 0, and both of them 1, and just always take the right one. So I think this is stupid. Oh, that's a nice solution with algebra, yeah. But let's go to smarter problems, I guess. Oh, I think everyone was accepted on main tests for me. So that is nice. Let's go to D. Okay. So in this problem, problem D, we are given an empty graph, like 1, 2, 3, 4, 5, 6, 7. And we have operations of a type, we have operations AI, DI, and KI. And this operation means that I start from some AI, and then I add an edge to like the number that is in the distance di from me. So if I, for example, have like 2, 2, 2, sorry, 2 to 1, let's say, then what I do is I add the edge to the next one, add the edge to the one that is like this is distance, this is how many times, and this is starting point. I add the edge to the one that is like at the distance d from me, and I do this k times. So for example, if k would be equal to 2, then I will also do this like one more time, like this, right? This is how much time I do this. Or well, maybe if there will be 3 here, then I won't add any edge, because this would go out of our array, right? So I have many of those operations of like adding edges to like vertices that are like d far from each other, and I want to say how many connected components do I have in the end. So now we can do union find, and we can wonder when there is an edge between two guys. Like the most important constraint in this task was di smaller than 10, or like smaller or equal to 10. So we can look for some di, and basically let's say that I am in some I, and here I have I plus our distance that now I am like looking at. So for example, now I am looking at distance 5, so I want to say between which, if I look at the distance 1, then I have those possible edges, right? Like to 5, to 7, through 8, and I want to say which of those possible edges are there, and if there is some edge, then I union find them using union find. Or you can just do this with DFS, but I prefer union find. So let's say that we have I and let's say that I have I and I plus d, right? And I want to check if there is an edge between them. Like if there is an operation that adds edge between them. How to do this? Well, to do this, we need to check if there is some update. Like this update, what it does, it just takes like this interval and add edges between each adjacent. So we need to check if there is an interval such that it has both of them. The interval for d, obviously. Right? Okay. So how to do this? We can just do simple prefix sums and add and add like when we have this update here, we would like to add one here and add one here, and this is it basically. What does it mean? It means that, or let me explain it one more time. Like we want to check if there is an edge between I and I plus d, right? So when we have some update, and let's say that this update is jumping by 3, like this. What we would like to do is like add one here, add one here, add one here, add one here. And this would mean that basically we are just, for each of those numbers, we are adding the edge to the next one. Obviously we are solving this problem for d equal to 3 now, right? Because we will solve it for each d. We'll solve it offline or something. And when I have added 3 everywhere here, well, here I will not like to add here. So we can just do prefix sums. Like we can just add one here and subtract one here and just do prefix sums of this array. And then we will see that, well, for each guy here we'll add one, and for each guy here we'll add nothing because we already subtracted one. Obviously we are doing these prefix sums like not s from I is equal to s from I minus 1 plus something. We are doing s from I is equal to s from I minus d here, right? Because we are jumping by d. And this is basically what we are doing. If our guy has a number greater than 0, then we are adding edge to the next one. And also you can you can solve it without DSU. You can just add those edges to some graph and then just do DFS, because you have just 10 times n possible edges. Yeah, sorry, d times n. So, do you have any questions? Sorry for saying it so briefly. Yeah, you can see my implementation. I think it wasn't even this bad. So basically I am reading queries, and what I am doing, I am adding to those prefix sums and subtracting from these prefix sums. Here I am keeping for which distance this is. Here I am keeping my union find. And well, here I am like calculating these prefix sums for each d from 1 to 10, right? And if my prefix sums, as I said, is greater than 0, then I am merging myself with the next one, or unioning myself with the next one. And then here I am keeping the amount of components. Yeah. Because yeah, this is like a known trick. If you like have some array 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and for each, and you want to add, let's say, to 2, you want to add with distance of 2, then you can just do a prefix sums that jump 2. So you do s from I is equal to s from I minus 2 plus value from I, not jumping by 1. You want to do prefix sums jumping by 2, and just add 1 here and subtract 1 here. And when you will do prefix sums over this, then you will like add 1 to each guy on this interval. Yeah. And this is working. Yeah. Okay. I don't see any questions. So let's go to problem E. This was like the worst problem for me, because well, my solution to it is like n times this number, like this 2 to the power of 10. But the problem is that, well, I did not think it will go accept. But why the constraints are so big? Okay. So in this problem, we have n numbers, a1, a2, up to an. And for each number, we have a probability pi, right? Given in some form. And then for each number, with this probability, we add it to our multiset. So for example, we will add a1, a3, and a5. Like with each number, with this probability, we are deciding if it goes into set or out of the set. And then for this set, we are calculating its XOR. And we are squaring it. And we want to find the expected value of this number. Right? So, like, what will be this expected value? It will be just sum over all possible sets. Yeah, it will be like sum over all possible sets, right? Over this value, over XOR squared. Yeah, divided by the number of possible sets. Number of possibilities. Yeah. This is how expected value works. We are summing the terms and dividing by the number of terms. So, if you would, for example, have like sum, so you would have a1 plus a3 plus a5 squared. Then you could just do some trick and like notice that basically we are like picking every pair and we want to find the expected value of that. But with XOR you don't have any tricks like this. Like if we just have XOR, then maybe we could do some tricks, but if you have XOR squared, then it's like bad. So we just have for each XOR here calculate like how many different what is the probability that we'll get this XOR, okay? This is basically what we want to calculate. And well, this is a simple DP. If I do DP from I from XOR, so assuming that I only look at the A1, A2, AI array, right? How probable is that I will get XOR X, let's say? How possible is that I will get XOR X? Well, I can look at I minus 1. And just, I will either draw my number into multiset or not. So it will be either dp from I from X XOR AI. So I either draw my number, so I XORed with it, or I haven't. And probability that this will happen is just pi, and probability that this will happen is 1 minus pi. And this is basically it. We are summing those two. And then in the end, our answer will be sum over dp n x times x squared, because this is probability that we'll get this XOR times this XOR squared, divided by like 1. Oh no, this is just it basically. Yeah. The probability that we'll get something times this. This is how we calculate expected value. I don't know how to like explain it differently. So I will repeat. For each XOR we want to calculate what is the probability that we'll get it in the end. We do a simple DP. For each prefix we calculate what is the probability that we'll get XOR X. This is up to 1023, sorry. And we have two different options. Either we draw our AI and then we have to XOR with it, and the probability that this will happen is pi, or we don't draw our AI, so well, our XOR doesn't change, and we have 1 minus pi probability that this will happen, right? And then in the end, to get expected value, we are just summing over all possible XORs. We are taking the probability that we'll get this XOR times this XOR squared. Because this is what we want expected value of. We want expected value of SS squared. So, do you have any questions? This is like, if somebody ever did a problem with expected value, this should be like obvious to you. And I think there are some great blogs on Codeforces about expected value. Thanks. If you have any questions, then please ask them. Yeah, maybe I will repeat even the third time, because yeah. We want to calculate the expected value of XOR squared, right? So to do this, for each XOR, we'll calculate what is the probability that we'll get it. And as we know, our expected value is just sum over p from XOR times XOR squared. Well, this is just our expected value, right? So to calculate for each XOR what is the probability that we'll get it, we are just doing dp over all prefixes over x, right? And well, we have two possibilities. Either we take AI or we don't take it, and we have to multiply it by according probabilities. Yeah, and this is just it. So I think everything that I got accepted, so I will get to master. I think that is nice, because yeah, it is accepted on main tests. I will get over 2200, I think. So yeah, that is quite nice for me. And I think thank you for watching this stream. There will be blog with those explanations, and you will be able to ask questions below the blog. So I think this will be nice for you. And yeah, it got accepted on main tests. This solution was not expected. Well, let's see. Oh, yeah, this was not expected, definitely. Because my solution is much smaller. Sorry, my solution is much slower. Yeah, that's nice. That is quite funny, because my solution is much slower than this. Let me read. Yeah, this is something different. You can also read it. Yeah. So this is me on Codeforces. I think thank you for the stream and see you next time. Or do you have any questions? That is quite funny that I've got like a different solution. And yeah, it's funny that it got accepted, right? Well, yeah. It's very weird. For sure. See you next time and wait for the blog. Well, I don't know how to solve f, so you can just look at the tutorial and try to solve it. Bye.